Hi everyone, in this screencast I'm going to go through looking at rectangular and triangular PDFs and comparing them to Gaussians and also combining them, like rectangular with rectangular and things like that, and kind of seeing what the outcome is. So the first thing I want to do is just kind of look at a rectangular PDF. So over here you see that I've got a histogram of what looks like kind of a rectangular PDF. The area is not normalized to 1. The area is just, it's a histogram with frequency down the side. And where this comes from is I made a bunch of data using Monte-Carlo simulation, but not using a Gaussian like we did in the past. Instead, I used something with an input mean of 3 and an input half width of 0.1. So over here, that means the peak is at, or not the peak, but the middle is at 3, and then it goes to 0.1 away from that on either side. So 2.9 on one side and 3.1 on the other. If we look at the standard uncertainty, like we discussed in class, the standard uncertainty is going to be 0.1 divided by square root of 3. That's going to be the standard uncertainty. And so I simulated a whole bunch of that data. If you care, this is, or if you're interested, I guess, this is what the function looks like to make square data out of those two parameters. And after I've done that, if I take the mean of all those data that I produced using the simulation and take the standard deviation of all those data, you see that the standard deviation of all those simulated data that have a rectangular distribution, all those simulated data have a standard deviation of 0.058, which is the same as the standard uncertainty, right? So this is what we're looking at in class. We're basically saying using that a divided by the square root of 3 is the thing that actually gives you the standard deviation of the rectangular distribution. Now, if I also simulate a Gaussian that has that same standard uncertainty, I also get something with a mean of 3 and a standard deviation of 0.05, not 7, just because you know how the random numbers change every time you change something a little bit, but these are close enough to believe that they're effectively the same. So both of these have the same standard uncertainty, which is 0.057 or 8. And so this is if you kind of compare the same histogram and Gaussian using the same x bins and axis. This is kind of what the two would look like. So this is the rectangle that would have the same standard uncertainty as the Gaussian. Okay, moving on to a triangle, and Gaussian would do the very same sort of thing. The triangle is going to have an input mean of 3 and is going to have a half width of 0.1, which means the standard uncertainty for the triangle is going to be that 0.1 divided by the square root of 6. So I simulate that, and this one's a really crazy function, but it does in fact make triangular data, and you can see that from the histogram shown over here. The mean of that, of those data is 3, and the standard deviation of those data is 0.041, just like we were expecting from the standard uncertainty that we calculated. Again, if we repeat and do the Gaussian that has that same mean and standard deviation, we get, so this is the input standard deviation, and I use that to make my Gaussian data, right? So there I use that mean and that standard deviation, and I get still the same, I get 3 and 0.04. And then if I kind of compare what my triangle and my Gaussian look like compared to each other, they look pretty similar. The big difference is that there's this kind of this tail with the Gaussian that just doesn't exist with the triangle. And of course, if I simulated enough data, you'd see the triangle's a little bit more peaked. Or the very peak is very, well, it's a triangle. Now let's take a look at combining rectangles. So what I did is I generated two rectangles that are basically the same. So they have an input mean of 3 and input half width of 0.1, just like the one on the first page. So that's what this one over here looks like. Make a second one that looks exactly the same. And then what I'm going to do is I'm going to add them up each of my simulated points, I'm going to add it up, and it's going to give me z, which z is equal to x plus y. Now, if I do that, and then I simulate just a whole bunch of, I do that and I simulate a whole bunch of data points, what happens is I can then take my regular mean and my regular standard deviation of the simulated data points, and you see that the mean of the z is equal to x plus y, so rectangle 1 simulated data point plus rectangle 2 simulated data point, and a whole bunch of those. The mean is basically 3 plus 3 is 6. The standard deviation of that distribution is going to be the uncertainty when we combine those previous two uncertainties. So the standard uncertainties are 0.058. There's two of them. If we use our standard uncertainty propagation equation, right, we get that the uncertainty in z would be the square root of the sum of the squares of the uncertainty. So dx squared plus dy squared, square root of that gives us dz, right? So that's if we calculate it just from the standard uncertainties over here. That's what we calculate here. Or we simulate some rectangular data and calculate the standard deviation of those two. Okay, well, they look like the ones above. But also, if I simulate those data and I add them up, and then I calculate the standard deviation of those two, you see that I get the same standard deviation. So all these different ways of finding that when you combine the uncertainties, you're adding them in quadrature. And this is also kind of showing that despite the fact that we're using square distributions, the same sort of rules for adding uncertainties apply. Now, one of the really interesting pieces is that when I combine these two rectangles, this is what my z column looks like. So this is all my data in this column. When I actually plot those data as a histogram, this is what they look like over here. So they actually look somewhat Gaussian. Not exactly Gaussian, but they look somewhat Gaussian. And if you combine, if you keep on combining more rectangulars and more triangles, or even with a Gaussian, this becomes more and more Gaussian. So it looks very reasonable that what we're doing is approximating our rectangular distributions as Gaussians when we're doing our uncertainty propagations. Now I can also look at combining a triangle and a rectangle. So when I combine a triangle and a rectangle, these are basically the triangles and rectangles that we had from the very first two tabs. And when I combine them, so I've got a rectangular distribution, which gives us a standard uncertainty of 0.058. That's this one. I have sorry, did I say triangular? There's a rectangular. I have a triangular one that gives us a standard uncertainty of 0.041. That's this one. And when we combine those, we do some simulated data, and then we add them up, and we get, well, first of all, the standard deviation of that is 0.071. If we compare it to the calculated standard deviation, if I had just used the standard uncertainties as the a over root 3 and a over root 6, I would also get this 0.071. So again, the simulation is giving us the same sort of information that our standard uncertainty propagation calculations are doing. And very similar to when we were combining the rectangles, we see if we combine a rectangle and a triangle, we get something that looks somewhat Gaussian. So basically, as soon as we start mashing triangles and rectangles and Gaussians together to do uncertainty propagations, those different types of PDFs, we get things that come out in Gaussian, which again makes it very reasonable that we're basically approximating all these things as Gaussians when we are doing these calculations. The final one, just to look at a different type of function, is looking at actually doing a product. So I've got a rectangle with input mean of 3, half width of 0.1, that's this one. I've got another rectangle with input mean of 2 and half width of 0.05, that's this one. And I'm going to take the product of those two, so I simulate a whole bunch of data for both of those. And what comes out the other end is something that has z is equal to x times y, and it's roughly 6. So that's the mean of all these data down here. Standard deviation of all these data is shown here. So that's the standard deviation of all these data below. And if I were to calculate the uncertainty, which should be the same as this standard deviation of the simulated data, using our uncertainty propagation equation, this one over here, I get the same value that we have from the simulation. So great, this is working also when we do products, and you see that when I do the product and I histogram it, I also get something that looks fairly Gaussian. Note that in this case, the scale on this axis is not the same as the scale on the axis of the two ones above, where it was on the previous two tabs. So hopefully that makes some sense and gives you a sense of what happens when you start manipulating square PDFs and triangular PDFs, and you start mashing them together, multiplying them, adding them, or even combining them with Gaussians, and how they compare to Gaussians having the same standard deviation.